In this video, I want to talk about the quotient rule for square roots. Now, students often find this much more difficult than previous lessons, and that's understandable because dividing is usually more complicated than multiplying, right? So let's look at the general rule, one that you might find in the textbook. A over B is equivalent to the square root of A over the square root of B. This is very similar to the product rule, and that we're allowed to break up the square root individually, just like we did with multiplication, but now we're doing it with division. Okay, but the thing I want to mention again is that because these are equivalent statements, you can go either way. And there will be some problems where you'll want to go one way and some problems where you want to go the other way. I'm going to show examples of both, but I want you to keep that in mind. Since these are equivalent statements, you can go either way, whichever would be more convenient for you. So the first example, I want to somehow simplify this problem. I have the square root of 2x squared over 9y to the fourth. Okay, well, how am I going to simplify this? If I can, I want to simplify it before I start using the quotient rule, but it doesn't look like I can because 2 over 9, I can't simplify. X with y, there's nothing to be done. Okay, so I'm going to break this up with the quotient rule and see if I have any more luck that way. So 2x squared over square root of 9y to the fourth. Okay, from here, is there anything I can do? Well, the square root of 2, not much. But I can break this up by the product rule and see I will have some luck with x squared. Also, the square root of 9 and the square root of y to the fourth. Okay, so it looks like I am going to have some luck here. I'm going to come down here. Now, the square root of 2 is the square root of 2. There's not much to be done there, but the square root of x squared is x. So this is going to be square root 2 x. X is outside the square root. The square root of 9 is 3 because 3 times 3 is 9. And the square root of y to the fourth would be y squared because y squared times y squared is y to the fourth. So this is, as ugly as it is, this would be the final answer. So this is the final answer that I would put in. All right, let's go into another example. Now, this one is kind of already using the quotient rule. So I have the square root of 234 times x to the 11th times y, and that's over the square root of 26 times x to the 7th times y. I'll go ahead and give you a little hint. If you see a problem in a math class and it's already broken up for you, you probably want to go the other way on the quotient rule, and that's probably what's going to happen. Now, more strategically, these two are even numbers. Here I have x to the 11th, I have x to the 7th, y. I can do some reducing here. So I'm going to use the quotient rule going the other way, and I'm going to put them all inside the same square root and see if I can't simplify before I start breaking this up. All right, well, 234 over 226, they're both even, so I can at least take a 2 out, but actually 9 times 26 is 234, so I can simplify that by quite a bit. Now, by the quotient rule of exponents, I have x to the 11th over x to the 7th, so that would be x to the 11 minus 7, and 11 minus 7 is 4. Okay, then I have y to the first over y to the first, so this would be y to the 0th, because 1 minus 1 is 0, but that's just 1. Okay, now I can break this up. So what times what would make 9? 3. And this would be x squared times x squared would make x to the fourth. So this would be x squared. So that simplified quite a bit. Okay, so in this way, we use the quotient rule going the opposite way that it's given in the textbook. But that's okay. It's equivalent statements. You can go either way. All right, so hopefully that helps. In this next example, we can see it's a very similar thing where it's already giving us the quotient rule split up this way. So I would say you probably want to go the other way. And even more strategically, you have 9 over 3, so you can simplify a to the 5th over a fourth. simplify, and then a to the 14th, or b to the 14th over b to the 5th. So let's put them all inside the same square root by quotient rule. Let's see what we get. Okay, from there, I got 9 over 3, so that takes it to 9, or that takes it to 3, excuse me. And a to the 5th over a to the 4th, so that's 5 minus 4, that's just 1. And 14 minus 5 is going to be 5 and 4 is 9. All right. So, now we can break this up by the product rule. And you may be tempted to say, oh, well, this is a 9, so it turns into 3. But be careful, because it's not going to quite work. Doesn't work with exponents that way, in case you were thinking that, but I don't know that you were. These are not going to be able to split up, so I'm going to put them back together. And what can I do? I can break this up as b to the 8th times b, and then this isn't going to work. That's going to be b squared 4 times. So I can have b to the 4th root 3a times b. Okay, so that would be my final answer. So there's one thing I should mention, and it's a really slick trick, but once you get used to this, you will see that if you have an even number of exponent, so some n where this n is an even number, pick an even number for me. Let's say you pick 6, you're going to learn that it actually just cuts it in half. Okay, so when you get practice, you'll notice that these are just cut in half. We're going to go over that later of how we can view this and how that might make sense. But right now, I just want you to notice that as you play, it's always going to make that even. Now, what about odds? Well, if I subtract 1, that's even. So that would be x to the 10th times x. So I can cut this in half times root x. Okay. Now, that's just, kind of noticing how these things work. But as you play with this, as you do your homework, try to notice that, because that would really save you some time. All right, the next thing I want to talk about is rationalizing the denominator, which sometimes seems kind of picky that we would make students do this, but it is great practice for something that you're going to learn later. So I think it's very valuable. It's kind of frustrating because you don't know what that later is, but anyway. Now, what do I mean by rationalizing the denominator? If there's a square root in the denominator, we don't want to answer that way. We only want to answer with square roots in the numerator, up top. So what we can do is we can multiply both top and bottom by that square root. And so I get a times the square root of b over root b times root b, which is b. Okay. And so these are equivalent statements. Now I'm going to write it a little bit neater so we can see the final answer. This is b equals a root b over b. All right. Okay, so this is rationalizing the denominator, is getting that square root out of the denominator. It seems kind of picky that we have to answer in this way, but again, it's going to lead to something that's way more complicated in Chapter 2, so this is good practice. So here I picked an example, and you have 2 times root 3 over 3 times root 10. We want to get that square root out of the denominator, and the way I can do it is I can multiply both top and bottom by that square root 10. Okay, so let's see what happens. I get 2 times 3 times 10 over 3 times 10, because the square root goes away when you multiply the same thing, so you just get 10. All right, so I have 2 root 30 over 30. And then if I can, I want to simplify this square root 30, but I'm not going to be able to do that because there isn't a perfect square in there. And then I can reduce this fraction. I have 2 over 30, so I can cut the 2, cut this in half, and 15. So my final answer is going to be root 30 over 15. All right. All right, so hopefully that helps. Again, we're trying to get the square root out of the denominator, and so what I did is I multiplied both top and bottom. I can do this because it's the same thing over itself, so it's just equal to 1, and then we're able to reduce it. Let's try another one to make sure that makes sense. So I have 12 times root 3 over square root of 2. So let's see if we can't get that square root of 2 out of there. So I'm going to multiply both top and bottom by the square root of 2. And what happens? I get 12 times 3 times 2 over, and then that's going to just be 2, because square root times square root, it's just whatever's inside. All right, well, if I simplify that, what do I get? 12 times root 6 over 2. If I can, I want to simplify that square root 6, but I can't because there isn't a perfect square. But I can simplify 12 divided by 2, and what's 12 divided by 2 but 6? So this is going to be 6 root 6, all right? All right, so hopefully that helps. Again, the goal is we're trying to get that square root out of the denominator, and we can multiply it both top and bottom by that, all right? Now, the next thing is conjugates. I want to explain what a conjugate is because we need this for more complicated rationalizing denominators. So, the conjugate of a plus b is a minus b. We're just going to flip the sign to make a conjugate. Okay, what is a conjugate? It's just, again, the opposite sign in the middle. That is to say, if it was a minus b, the conjugate would be a plus b. And you might be thinking, okay, what's a conjugate? Oh my god, well, this doesn't make any sense. Why would you do this? You would do it because of this problem. If you have 4 over 1 plus square root 5, I can't simply just multiply both top and bottom by the square root of 5. You'll find that that doesn't actually take the square root out of 5. If you distribute this, you're still going to be left with the square root 5, so that doesn't help. We're going to have to multiply this by the conjugate. So 1 minus root 5, 1 minus root 5. This is going to work, okay? So using the conjugate will help us if we have addition or subtraction here. Okay, let's distribute it and make sure that this actually works. So 4 times 1 is 4. 4 times negative root 5 is negative 4 root 5. And that's it. And then we have 1 times 1, that's 1. 1 times negative root 5, negative root 5. 1 times root 5 plus root 5. Root 5 times negative root 5 would be negative 5, right? Because it's times itself, so the square root goes away. You'll notice that these are equal and opposite, so they cancel. And now we're left with 4 minus 4 root 5 over 1 minus 5. Okay, we're almost done. And what's 1 minus 5 but negative 4? So I'm going to rewrite that just from my space. And I'm going to actually split the denominator so I can simplify this. So this is 4 over negative 4 minus 4 root 5 over negative 4. And you can see I can simplify this to negative 1, and I can simplify this to positive root 5. Let's see if I can put that in there. Negative 1 plus root 5. And that's the final answer, okay? So again, there's more steps. We have to distribute, but we want to make use of that conjugate. We want to make use of that conjugate so we can get rid of it, okay? Again, I used kind of a fancy trick. I split the denominator because I saw that I could simplify. You might say, okay, well, you can cancel this out, and that's fine as long as if you cancel it, as long as you watch your signs. Let's look at another example and make sure that we understand this. So I have 7 over 2 plus root 3. Again, I have this separation of addition, so I'm going to have to multiply it by the conjugate. Fancy word for has to have the opposite sign in the middle. All right, let's do it. So 7 times 2 is 14. 7 times negative root 3 is negative 7 root 3. 2 times 2 is 4. And then negative 2 root 3 plus 2 root 3. And then that's going to be negative 3. Again, I notice that these are equal and opposite, so they cancel. It's always going to work that way, so that's really handy. I'm left with 14 minus 7 root 3 over 4 minus 3, but 4 minus 3 is just 1. Okay, so that means I have the final answer, 14 minus 7 root 3. Awesome. That's it. It's that easy, or it's that hard, depending on your standing on it. But that's what you do. So again, conjugate, fancy word for switching the sign in the middle. If you do this, you'll notice that these cancel and you'll get rid of that square root. You do not have to do it for problems like this one. This one. So you don't have to do it for this because this was multiplication. So I don't have to use a conjugate that way. I didn't have to use it in this problem either. It's only when you have addition or subtraction in that denominator that you have to do it. Okay? It's kind of challenging at first, but hopefully you get the hang of it through some practice. And please let me know if you have any questions, okay? Bye.